Imagine discovering a second Earth, a planet with oceans and atmosphere, perhaps even forests and life. Now imagine knowing that no human will ever set foot there. This is not pessimism. This is the brutal reality that physics, biology, and the vastness of space have imposed upon us. The universe has teased humanity with the promise of habitable worlds, but reaching them may remain forever beyond our grasp. In 2016, astronomers announced one of the most exciting discoveries in the history of space exploration: Proxima Centauri b, a rocky planet orbiting within the habitable zone of our nearest stellar neighbour. At just 424 light-years away, it seemed tantalizingly close. Since then, we have discovered thousands more exoplanets, with dozens potentially capable of supporting life. Teagardens Star b at 12.5 light-years, Wolf 1069b at 31 light-years, the TRAPPIST-1 system, with 7 Earth-sized worlds at 40 light-years. The universe, it seems, is littered with potential new homes, but here is the cruel irony. The very proximity that makes these worlds exciting is an illusion created by cosmic scales. What appears close in astronomical terms represents distances so vast that our minds struggle to comprehend them. And as we will discover, even the nearest habitable world might as well be on the other side of the universe. To understand why we will never reach another habitable world, we must first grasp just how immense these distances truly are. Proxima Centauri b, our closest potentially habitable neighbour, is about 40 trillion kilometres away. This number is so abstract that our brains simply cannot process it. Let's try a different approach. If you were to drive a car at 100 kilometres per hour without ever stopping, it would take you over 45 million years to reach Proxima Centauri. That's longer than the time since the dinosaurs went extinct. The fastest spacecraft humanity has ever built, the Parker Solar Probe, reaches speeds of over 700,000 kilometres per hour when close to the Sun. An impressive feat. And yet even it would take about 6,300 years to travel to Proxima Centauri. That's longer than the entire documented history of human civilization. Let's consider a more realistic scenario. The Voyager 1 probe, which has been travelling since 1977 and has now reached interstellar space, is moving away from the solar system at about 61,000 kilometres per hour. At this speed, it would take more than 73,000 years to reach Proxima Centauri, assuming it were even travelling in the right direction, which it isn't. And remember, Proxima Centauri is the closest star. The TRAPPIST-1 system, with its 7 potentially habitable worlds, is nearly 10 times farther away. At Voyager's speed, reaching it would take over 700,000 years. The fundamental problem is the relationship between speed and distance. To complete an interstellar journey in a human timescale, say in a few decades instead of millennia, we would have to reach speeds that are a significant fraction of the speed of light. At least 10 to 20% would be needed to reduce travel time to under a century. But this is where physics begins to crush our dreams. The energy requirements for interstellar travel are not merely challenging. They are astronomical in the truest sense of the word. Scientists have calculated that to send even a small probe to the nearest star at 20%, the speed of light would require energy, equivalent to 100 times the total annual energy output of the entire world. And that's just for a probe weighing a few grams. Now consider a spacecraft capable of carrying humans. The Apollo Command Module weighed about 29,000 kilograms. To accelerate such a craft to 20%, the speed of light would require approximately 2.9 million gigawatts of power, almost double the entire energy consumption of India in a single hour. And that's just for acceleration. Deceleration at the destination would require the same amount of energy again. This problem is known as the tyranny of the rocket equation, and it mercilessly exposes the limitations of conventional propulsion technology. The heavier the spacecraft and the higher the desired final speed, the more fuel is required. But this propellant itself has mass, which also needs to be accelerated, requiring even more propellant. Calculations show that even with the most efficient conceivable chemical or nuclear propulsion systems, the amount of propellant required exceeds any practical limit. A spacecraft would need to consist of more than 99.9% fuel just to reach a fraction of the necessary speed. But even if we somehow solve the energy problem, we encounter an absolute limit: the speed of light. Albert Einstein's theory of relativity shows us that nothing with mass can travel at or faster than light, about 300,000 kilometers per second. This isn't a technical limitation. It is a fundamental law of the universe. The closer an object gets to the speed of light, the more energy is required to accelerate it further. As we approach that cosmic speed limit, the energy requirement approaches infinity. Even if we could harness all the energy of a star, it would be mathematically impossible to propel a spacecraft with people on board to the speed of light. Various exotic propulsion concepts have been proposed over the decades. Nuclear pulse propulsion, where a spacecraft is pushed by nuclear explosions. Fusion ramjets that collect hydrogen from interstellar space. Laser sails that ride beams of light. Antimatter engines that annihilate matter for pure energy conversion. Warp drives that bend space-time itself. Each of these concepts either violates known physics, requires technology centuries beyond our current capabilities, or demands energy sources that simply don't exist. The most promising near-term concept, the laser sail, could theoretically propel a tiny probe weighing just a few grams to 20% the speed of light. This is the vision behind Breakthrough Starshot, a project that aims to send nanoscale spacecraft to Proxima Centauri within our lifetimes. But even this revolutionary approach faces enormous challenges. The laser array would need to be kilometers wide. The sail would need to survive acceleration forces millions of times stronger than gravity. And at 20% of light speed, even a grain of cosmic dust would strike with the force of a bomb. And crucially, a spacecraft weighing just a few grams cannot carry humans. It cannot even carry enough instruments to properly study a planet. Scaling up the technology to carry people is not merely difficult. It may be fundamentally impossible. Assuming we could somehow solve all the propulsion problems, a new nightmare begins, the journey itself. A trip to even the nearest habitable world would take decades at best, centuries at worst. During this time, everything that could go wrong would have endless opportunities to go wrong. Life support systems would need to function with absolute perfection for generations. Water, food, and oxygen would have to be recycled in a completely closed-loop system without a single critical failure. On the International Space Station, which orbits just 400 kilometers above Earth, where rescue is always possible, equipment malfunctions regularly. Astronauts can receive resupply missions and emergency evacuations. On a journey to another star, there would be no backup, no rescue, no second chances. Then there is cosmic radiation, an invisible killer that would bombard the spacecraft continuously for years or decades. In interstellar space, there is no protective magnetic field like on Earth. Astronauts would be exposed to radiation levels 700 times higher than on our planet's surface. That's equivalent to hundreds of CT scans every year. The risk of cancer would increase by 5 to 10%. The cardiovascular system would age decades faster than normal. The brain would suffer measurable cognitive damage. Memory, problems, slowed thinking, difficulty making decisions. All of this damage would accumulate year after year with no way to stop it. Conventional shielding provides little protection and even creates new dangers. When high-energy particles strike heavy shielding materials, they produce secondary radiation that can be even more harmful than the original cosmic rays. Making the shielding thick enough to provide real protection would make the spacecraft impossibly heavy to accelerate. The human body itself would deteriorate in ways we are only beginning to understand. Studies of astronauts on the International Space Station show alarming changes after just months in space. Bone density decreases by 1 to 3% per month. Muscles atrophy at similar rates. The heart shrinks by up to 20% as it no longer needs to pump blood against gravity. Eyes change shape, causing permanent vision problems. The immune system weakens. All of this occurs in just 6 months, with daily exercise and the possibility of returning to Earth. A journey lasting decades would transform the human body into something barely capable of surviving. Communication presents another insurmountable challenge. Even at the speed of light, the fastest possible form of information transmission, signals would take over 4 years to travel from Proxima Centauri to Earth. A simple radio message and its reply would take over 8 years. Real-time communication with home would be impossible. The crew of such a spacecraft would be utterly alone, without the possibility of seeking advice or assistance. If a crisis occurred halfway to the destination, Earth would not even learn about it until years after it happened. And then there is the final barrier: navigation and survival at relativistic speeds. Interstellar space appears empty, but it is filled with dust, gas and tiny particles. At speeds of 10 or 20% the speed of light, even a particle the size of a grain of dust would strike with the force of a hand grenade. A larger object could destroy the entire spacecraft instantly. At such velocities, evasive maneuvers would be virtually impossible, and detecting obstacles in time to react would pose an enormous technological challenge. But let us assume, for the sake of argument, that we overcome every single one of these obstacles. We develop impossible propulsion systems, we solve the energy crisis, we create perfect life support and radiation shielding. We cross the void between stars. What awaits us at our destination may be the cruelest disappointment of all. The potentially habitable exoplanets we have discovered are almost exclusively orbiting red dwarf stars. These small, cool stars are the most common in our galaxy, which is why we keep finding planets around them. But red dwarfs are hostile to life in ways our sun is not. They are notorious for producing intense stellar flares, violent eruptions of radiation that can bombard nearby planets with ultraviolet and X-ray, energy hundreds of times more powerful than anything our sun produces. Because red dwarfs are so dim, their habitable zones are extremely close to the star, typically 10 to 20 times closer than Earth is to the sun. This means any planet with liquid water must orbit directly in the path of these devastating flares. Research has shown that red dwarfs remain magnetically active and prone to flaring for billions of years. Recent studies have discovered that even old red dwarfs like Barnard's star, which is 10 billion years old, still unleash scorching flares about 25% of the time. The consequences for habitability are devastating. These flares strip away planetary atmospheres over time. Without an atmosphere, liquid water cannot exist on a planet's surface. The TRAPPIST-1 system, once hailed as our best hope for finding life, now appears far less promising. Observations have shown that at least 2 of its planets, TRAPPIST-1b and TRAPPIST-1c, are bare rocks with no significant atmosphere. The other planets in the habitable zone are unlikely to have retained atmospheres either. Even Proxima Centauri b, our nearest potentially habitable neighbour, faces this problem. Its host star produces frequent and powerful flares. Scientists have calculated that an Earth-like atmosphere on Proxima b could be stripped away entirely within just a few million years, a blink of an eye in cosmic terms. The planet may well be a barren, radiation-scorched rock. Most planets in the habitable zones of red dwarfs face another challenge: tidal locking. Because they orbit so close to their stars, gravitational forces cause one side to permanently face the star while the other remains in eternal darkness. One hemisphere would be an inferno of perpetual daylight, the other a frozen wasteland of permanent night. Only a narrow twilight zone might be potentially habitable, if the planet even has an atmosphere to distribute heat. The few potentially habitable planets orbiting sun-like stars are even farther away, requiring even longer and more impossible journeys. And we have no guarantee that any of them actually possess the conditions necessary for life. Science fiction has long proposed a solution to the distance problem: generation ships. These massive self-contained habitats would travel through space for centuries, with multiple generations of humans being born, living, and dying before the destination is reached. The idea is compelling in stories. In reality, it is a prescription for disaster. Such a ship would need to house a genetically viable population, at least several hundred to 1,000 people, to avoid inbreeding and genetic collapse over multiple generations. It would require agriculture, water recycling, an artificial atmosphere, and countless systems that must function flawlessly for centuries. A single catastrophic failure at any point would doom everyone on board. The psychological and social problems are almost unimaginable. How do you maintain motivation and purpose for a mission whose destination you will never see? How do you ensure that knowledge and skills are passed down through generations? What happens when conflicts arise and there is nowhere to escape, no authority to appeal to, no possibility of leaving? Historians and psychologists have studied isolated communities throughout history, and the results are not encouraging. Societies fragment, knowledge is lost, violence erupts. And these were communities on Earth, with the possibility of contact with the outside world. A generation ship would be a sealed bottle hurtling through the void, with no hope of rescue, no communication with anyone outside, and no guarantee that the destination is even worth reaching after centuries of sacrifice. The truth is sobering. Another habitable world remains out of reach for us, not just today, but for the foreseeable future. The distances are too great. The speeds we would need to achieve are too high. The energy requirements are too vast. The challenges of survival during the journey are too numerous. And the destinations themselves may not even be habitable when we arrive. This is not a failure of ambition or imagination. It is a confrontation with the fundamental laws of physics and biology. The universe is not built to human scale. It was not designed with our lifespans, our energy sources, or our fragile bodies in mind. The stars are beautiful and eternally out of reach. However, this does not mean the exoplanets we have discovered are worthless to us. Quite the contrary. With increasingly powerful telescopes, we can explore these worlds from afar. We can analyze their atmospheres, search for biosignatures, and learn about conditions on other worlds. The James Webb Space Telescope and future generations of observatories will give us insights that were unimaginable just a few decades ago. We don't have to physically travel to the stars to understand them. Perhaps there is a certain humility in that. The universe is unimaginably vast, and even our nearest stellar neighbours lie beyond our reach. It reminds us how small we are and how limited our capabilities remain on a cosmic scale. The best planet for us is the one we already have. Earth has a perfect score on any habitability index, and it is 0 light years away. Any technology capable of making another world livable could also be used to preserve and restore this one. It will always be easier to protect our planetary home than to pack up and leave for a new one. The habitable worlds among the stars will continue to fascinate us, inspire us, and challenge our understanding of our place in the cosmos. But they will remain what they have always been, distant lights in the darkness, forever calling to us from beyond an unbridgeable void. I hope you enjoyed the video. I would be very grateful for your support, and I look forward to seeing you next time.